All right. Good morning, everyone. So I think we'll get started. So today we'll be looking at chapter 8, linear momentum and collisions. Okay. So to start with, I would like to just remind you guys that homework 7 is due tomorrow. Okay. So tomorrow by midnight it's due. So make sure you get a chance to finish the homework by tomorrow midnight. All right, and then also there should be an SI section tomorrow at 10:20 in the library or the classroom. Okay. So let's get started. So in our everyday life, so for example, this year, if you are watching or if you are paying attention to like election campaigns, or if you are watching some sports games. So the word momentum is used very often in those events. Okay, but in physics, the momentum is actually defined differently. So we'll take a look on this today. Okay, how the momentum is defined. Now pay attention to the title here. It says linear momentum. Okay, so for right now, we'll just focus on linear momentum, and then later on, a couple of chapters later, we'll also talk about rotational or angular momentum. Okay, so when the object are moving in the circular or in the curve, then we'll talk about that later. Okay, but in this chapter, we'll focus just on the linear momentum. So that means objects moving just linearly. All right. So to start with, we'll look at a couple of events that involve when the velocity of an object changes rapidly. Okay, so for example, if you are watching the baseball game, you usually see the batters hit the baseball very hard. So then the baseball actually it comes in the velocity of it comes in one direction, right? When it's hit it after it's hit it, then it goes in the other direction. So in both ways, the speeds are very big. So sometimes it could be like 90 miles per hour, right? So although the speeds they are maybe close to each other magnitude wise, but they are in opposite direction. So that means that's a sign of negative. So then the change of the velocity actually doubles in that case. Okay, so that's a very rapid change in velocity. Also, in one of the homework examples, or in the some of you guys got this in the your first exam, if you drop a ball from a certain height and then the ball will hit the floor, so with the initial velocity going down, and then when it bounces back, the velocity comes in the upward direction. So that's also a rapid change in velocity. If you remember, the acceleration involved, it's like kind of in the thousand scale meters per second. Okay, so that's also in the rapid change of the velocity of the object. So let's take a look what happens during this rapid change of velocity by looking at Newton's second law. So Newton's second law says the force that the object received, and in this case, we will take a look at the average force. So F sub AV stands for average force. That should equal to the mass times its acceleration. And then the acceleration is defined as change in v divided by time t, okay? Or delta t if you want. So then force received is equal to mass times delta v over delta t. Now, if you multiply both sides by t, then you get F average times t equals to m times delta v. Okay, delta v means final velocity minus initial velocity. So then you end up with this expression over here. So F average times t is equal to m times v final minus m times v initial. Okay, so let me write this equation down on my paper here. So we'll refer to that a few times today. That equals to, now keep in mind that force is a vector, so you put a arrow on top of it. That equals to mass times final velocity minus mass times initial velocity. Okay, you also put the arrow on top of the velocities. All right, so we'll examine this equation on the right hand side and then also on the left hand side. Okay, one by one. So let's take a look on this side. So in this side, you can see that you have a quantity minus another quantity. Okay, so they are in the same manner here, like the mass times velocity. But this is mass times final velocity. This is mass times initial velocity. Okay, so then for the definition of the linear momentum, it's actually referred to mass times the velocity. Okay, so in the PowerPoint slide shows here. So for linear momentum, we use symbol P equals to m times v. All right, so you can see that because velocity is a vector quantity times the scalar quantity of mass, then the momentum should be also a vector quantity. Okay, so p equals to m times v. And the SI unit for momentum comes from the SI unit for the mass times the SI unit for the velocity. So it's kilogram times meters per second. Okay. And the momentum should have the same direction as the velocity. Okay. So that's momentum. So let's take a quick look one example here. I think this one is quite straightforward. So it says, what's the magnitude of the momentum of a 0.0053 kilogram marble whose speed is 0.65 meters per second? What's the speed of a 0.132 kilogram baseball whose momentum has a magnitude of 3.28 kilometers per second? So in both cases, it just asks us for the magnitudes of momentum, okay, and then the speed, which is the magnitude of the velocity. So this just involves the scalar form of the definition for momentum. So P equals to mv. Okay, so that's the scalar form without the arrow. That means we are just looking at the scalar quantities or their magnitudes. So let's take a look at this together. Okay, I think it's quite straightforward, simple one here. So on your end, if my screen, my video view doesn't, it like appears like small, you probably want to click on the view, click on speaker view, so that will bring it, so that will put you in the larger mode. Okay, so let's take a look here. So in A, it says the mass, okay, is given. And then the speed is given. So starting with this equation, P equals to mv, you are looking for the momentum. So then basically the mass times the speed, okay, will give you the momentum. So that will give you 3.4 times 10 to the negative 3, okay, in kilograms times meters per second, all right? That'll be your momentum, okay? B here, it says what's the speed of 0.132, so that's the mass given, 1.132 kilogram baseball. The momentum's magnitude is given, P is given 3.28 kilogram times meters per second. So what will be the speed? So starting from here, P equals to mv, you're looking for speed, so V then equals to P over M, okay? So then you'll be doing 3.28 kilogram times meters per second divided by 0.132 kilogram. All right. So that will give you the speed as 24.8 meters per second. Okay. All right. Let me know if you have any questions. Okay. You can interrupt me anytime. All right. So let's definition of linear momentum. Now let's take a look the Newton's second law again. So Newton's second law says force equals to net force equals to mass times acceleration. But actually, this is valid only when the mass is constant. Okay, I probably have mentioned this in class one time or maybe twice. When Newton proposed his second law, in his theory, he actually proposed that net force on the object is equal to change of momentum divided by change in time t. Okay. Now, most of the times, when you guys look at physics problem, the mass of the object is not changing. But in some scenario, the mass of the object does change. Okay, so for example, when the rocket is launched into air, so then the fuel is being consumed and then expel out the exhaust heat in the process. So the mass of the rocket actually changes over the time. And that change of the mass actually contributed to part of change of the momentum. Okay. So that's the major factor there actually gives the net force for the rocket to go into the air. Okay. So we'll go back to that at the end of this chapter. Okay. But in that scenario, the mass does change. Okay. So either way, if that's changing in mass or if that's changing in velocity, then you'll receive net force. Okay. So that's actually Newton's second law initially when he proposed. Okay. So this is a more general formula for the Newton's second law. Net force equal to change in momentum over change in time t. Okay, so if realizing that if we look at this guy here, okay, then we can multiply both sides by delta t. So then you have net force times delta t equal to change in momentum. Okay, which is consistent with this term, net force or average force times delta t. Okay, which is the left-hand side of the equation that I mentioned earlier. So if you look at my paper here, so that's this guy, okay? So then this, we actually define it as the impulse, okay? So we use symbol I that equals to force times the impact time delta t, okay? We call this impact time. So then that is equal to, or that impulse has a SI unit of newtons times per second because Newton comes from force, seconds come from the time, okay? And if you realize that force is a vector times the scalar quantity, so then for impulse, it should be also a vector, okay? So it's a vector form, it has the same direction as the force, as the average force. Now looking back at this equation on my paper here, earlier we mentioned, so if this is impulse, okay, this is change in momentum, so then impulse should have the same dimension also as the momentum. So then if you remember, momentum is in kilograms times meters per second for the SI unit. So then impulse should be also having the unit equivalent to this kilogram times meters per second. So newtons times per second is equivalent to kilogram times meters per second. Okay, and that's the case because remember, so if you look at my paper over here, so remember when we say newtons, okay, so 1 Newton, when we introduce force, 1 Newton is actually equivalent to 1 kilogram times meters per second square, right? So then newtons times meter is equal to kilogram times meters per second square times second, right? So 1 second here will cancel out the square second square in the denominator here. So then it becomes kilogram times meters per second, okay? Which is exactly this one shows is equivalent to that dimension or that unit, okay? All right, so let's move on here. So again, from Newton's second law, average force is equal to delta P over delta T. So then you multiply both sides by delta T. That gives you this guy, F times delta T equals to change in momentum. All right, so this is impulse, the I. So then I equals to delta P. Okay, so impulse received by the object is equal to its change in momentum. So this is the impulse and momentum theorem. So if an object receives an impulse, then its momentum will change. Okay, so simply like that. Now, when striking a baseball, the batter actually swings the bat. So why? It's because when he swings the bat, actually the contact time or the impact time when the batter strike with the ball is increased. Okay, so because he wants to change the momentum of the balls very in a very like dramatic fashion, so then he wants to the force he can exert is the same, right? Keeps the same, has an upper limit, but the contact time between the bat and the baseball can be increased by swinging the bat. Okay, so by doing that, then the impulse delivered to the baseball can be very large. Okay, So that's why when the batters actually swings the bat. So you can increase the impulse by either increasing the force or increasing the contact time, because impulse equals to force times the contact time t. Okay. All right. So let's take a look at one example here. So this one says when spiking a volleyball, a player changes the velocity of the ball from 4.2 meters per second to minus 24 meters per second along a certain direction. So this is assuming that the ball is just moving in one direction. Okay, so then you use the negative sign and the positive signs to indicate the directions. All right, so initially the ball has positive velocity and then it changed to negative velocity. If the impulse delivered to the ball by the player is minus 9.3 kilograms times meters per second, what's the mass of the volleyball? Okay, so I'll give you guys a couple minutes to try to see if you can solve for this. Okay, so basically you want to apply impulse and momentum here. Okay, so I equals to delta P. All right, and then you are given I, and then delta P will be equal to mass final minus mass initial. Okay, or mass final minus initial, put the difference in the velocity in the parentheses. So then this will be equal to that. Okay, so you should be able to solve for this. Okay, I'll give you a couple minutes and then we can take a look at the solution together. All right, I think I see a few responses in, so let's take a look at this one together, okay? So as I said, delta P is equal to M for V final minus MV initial. So then you can actually single out M, so and that should be equal to M times VF minus vi, okay? Final velocity minus initial velocity, and that should equal to, according to the impulse and momentum theorem, that should be equal to the impulse, okay? So it gives you the impulse as minus 9.3, so you just write that down, minus 9.3 kilogram times meters per second equals to the mass times the final, which is minus 24 meters per second minus 4.2 initial. Okay, so initial is positive, but you put a negative because it's subtracted from the final. All right, so then your mass should be equal to, so this two would be like minus 28.2 meters per second. Okay, that should equal to, divide both sides by that. So divided by 28.2 with the negative sign. So minus 9.3 over minus 28.2. Okay, kilogram times meters per second on the top, meters per second on at the bottom. So this gives you 0.33 kilogram for the mass. Okay, so the mass will be equal to that. And then I see most of you guys submitted the right answer there. Okay, so except one answer says 0.39. I'm not sure. Probably some number when you plug it in wasn't right, or maybe just a typo. Okay. Any questions you guys might have on this one? All right. If you are clear, let's move on here. So let's take a look on another example here. So this one says a cruise ship with a mass of 1.00 times 10 to the 7 kilogram strikes a pier at the speed of 0.750 meters per second. Okay, so yeah, I don't know what happened, but maybe a incorrect operation somehow by the captain. So it says it comes to rest 6.00 meters later with a constant deceleration, damaging the ship, the pier, and the tugboat captain's finances. It says calculate the average force exerted on the pier using the concept of impulse. Okay. The hint given is first calculate the time it took to bring the ship to rest. Okay. So let me see. I think I'm gonna to give you guys a few minutes here. I think maybe better to open the breakout rooms for you guys to have some discussion there on this one. So actually, this is a combination of the momentum, impulse, and momentum theorem, and with the kinematics. Okay, because the ship comes to rest at 6.00 meters after a constant deceleration, and then its initial velocity is given. So you probably would have to use the one of the equation of motions there. Okay, so let me just have 5 rows, and then I'll put you guys randomly into the rows. Okay. All right. All right. So I think you guys know how to do this by using kinematics and the second law. Okay, so you basically can solve for the acceleration of the ship and then multiply that by the mass to give that average force. Okay, but since we learned the impulse and momentum theorem today, we are going to see how you can actually solve the problem by involving impulse and momentum theorem here. Okay, so basically we want to use I equals to delta P, which means F average times delta T equals to the MV final minus V initial, okay? Or MV final minus MV initial. So in this problem, we are looking for this, right? We are given the mass, we are given the final, which is 0. The initial is the 6 meters or 0.75 meters per second, okay? And then the mass is given. So the only thing remains how to figure out delta T here. All right. Now let's look at the kinematic side. So you have 5 equations of motions. Okay. I'm going to just pick the x equals to v average or x naught plus v average times t. All right. Now because it says the acceleration is constant or deceleration is constant, so then v average is equal to 1/2 of v initial minus v final. Okay. So then you can set up the initial position to be 0. So then final will be the 6 meters. Okay, so then 6 meter, you can solve for t here or delta t. Let's just use t here instead of delta t. Okay, so then t will be equal to x divided by v average. Okay, so v average is that guy. So then 6 meters divided by 1/2 of the initial is 0.750 meters per second plus the final is 0. Okay, so that gives you 16 seconds for the time. All right, so then take the t equal to 16 seconds here. You should be able to solve for your average force. So average force then should be equal to mv final minus v initial. All right, divided by the t. Okay, so now it says the mass is 1.0 times 10 to the 7 times the final is 0 minus 0.750 meters per second divided by the 16 seconds. Okay, so that gives you your average force to be minus 4.69 times 10 to the 5th newtons. Okay, so the minus sign says this is in the opposite direction of the initial velocity. Initial velocity says positive, so then this is negative, okay? So if initial is to the right, then the initial velocity is to the right and the force on the ship is to the left, okay? All right. Any questions you guys might have, just let me know, okay? All right, if that's clear, then we'll move on to the next section on conservation of linear momentum, okay? So again, if we look at the Newton's second law in the original form of net force equal to change in momentum over change in time t, then you can see that if the net force is equal to 0, then the momentum should not be changing, okay? So then delta P should also be equal to 0. So that means if the net force acting on the object is 0, then its momentum should be conserved, okay? So that means you can say momentum final equal to momentum initial, so it doesn't change, all right? Now, a lot of times we have more than one object in the system. So if you have a system of multiple objects, okay, so then between objects, they might have internal forces between them. But if the external forces add up to be 0, all right, then the internal forces, because they, according to Newton's third law, any forces will coming as a pair. So then if you find one internal forces, you should be able to find another internal forces that's in the opposite direction but the same magnitude. Okay, so in that sense, all the internal forces should add up to be 0. Okay, so And that's always true. Okay, so if you have multiple objects in the system, if you are considering all the internal forces, they should add up to be zero. Okay, so then in that sense, if you have a system of multiple objects, then as long as your net force, all the external forces sum up to be zero, then the net force should be equal to zero. Okay, so in that case, the conservation of momentums for the system of the multiple object will also apply. So then, if you add up the momenta from each of the object initial, okay, that should be equal to the momenta from each of the components or of the object's final. Okay, so momentum final for each object add up should be equal to momentum initial of each object add up. Okay, now keep in mind that although the sum of momenta might be constant, but each individual object may have change in their own momentum. Okay, so for example, object one might lose some momentum to object two. So then its final and the initial is not equal to each other. So if you look at each individual object, okay, so that's the case. All right. Let's take a look. For example, if we have like two cars, okay, collision. If one car is stopping or is moving at a slower speed, and then the car behind it hit it. Okay, so then when this happens, all right, so then if you look at both cars as one system, so then the momentum should conserve because when collision happens, all right, it usually happens in the very short time of period. So then external forces can be ignored. All right, so then net force should be equal to zero. So momentum should be conserved. Now you'll see that this guy behind will lose some momentum, giving it up to the car in front of it. Okay, so then this car will gain momentum, but the sum of the momenta from both cars should equal to each other. Okay, so this car will have momentum change, this car will have momentum change, but the sum of the momentum from the two will remain the same. All right. Let's take a look this example here. So it says two ice skaters stand at rest in the center of ice rink. When they push off against one another, the 45-kilogram skater acquires a speed of 0.62 meters per second. If the speed of the other skater is 0.89 meters per second, what's this skater's mass? Okay, so they start with zero momentum because they are at rest, right? So the final momentum, one acquires this speed, so then m times that will be the momentum. Now the other one will have mass times what's the speed, okay? So I'll give you guys a few minutes to try to see if you can solve this, and then we can take a look at the solution together, okay? This time I think I will just have you guys work individually. All right, I think I see a few responses in already. Let's take a look at the solution together, okay? So let's say two skaters stand at rest initially. So before they push against each other, so let's say initial, so the initial momentum should be equal to 0, right? So the final momentum should be equal to, I'm going to call this guy as M1, this guy has as mass M2, and then V1, V2, okay? So that should be M1, V1 plus M2, V2, okay? So that's the final. Now, if you consider them as one system, so system of two objects, okay? So then if they push against each other, so then the momentum should equal to initial should equal to final because there's no external forces over here, all right? So in that case, you can set up that this guy plus, so Pi equal to P final, that means 0 equals to M1 V1 plus M2 V2, okay? So M1 V1 plus M2 V2 then should be equal to 0, okay? This is the final momentum. This is the initial momentum. All right, now we want to be careful about the signs of the V1 and V2 because um, you can see that when they push against each other, so one would gain speed of velocity in, say, in the right position or right direction, then the other one will gain the speed in the left direction, okay? So if this is positive, then this guy is going to be negative, okay? So pay attention to that. If you give one velocity to be positive, then the other one will be negative. So this guy should be negative here, all right? So then when you look up over here, look at the equation over here, when you plug in the numbers, now you have M1, V1, V2 as knowns, M2 is the unknown. So you are looking for M2, okay? So then you will be plugging 45 kilograms times 0.62 meters per second plus M2 multiplied by negative 0.89 meters per second. Okay, that goes to 0. All right. So if you don't do that, you probably get a mass that is minus, which doesn't make sense. Okay. So in this case, then you'll move, let's say this guy to the other side of the equation. So minus become positive. So 45 times 0.62 meters per second, then equals to 0.89 meters per second times M2. Okay, divide both sides by 0.89 will give you your M2. Okay, so that would be 31 roughly. I think 31.3 probably kilograms. That would be your M2. Okay, now so when you are having a collision problem, so this is not exactly a collision, but one push against each other. So then there's just internal forces over here. Okay, so given the contact, there's no external forces over here. All right. So then you can apply conservation of momentum. Okay. So when a collision also happens, as I mentioned earlier, so the contact time is small, so then you can assume that the external forces doesn't add extra impulse to the system. Okay, so then the system's momentum should conserve. All right. Any questions you guys might have? All right. So if not, then we'll just stop here for today. Okay, we'll come back Wednesday. All right. So
Dr. Ho, I had a quick question.
yes.
You had done a breakdown of the exam scores and between the two classes for the last exam. Are you planning on doing that again for this past one?
You're talking about it, the breakdown of the exams?
Yeah, yeah.
Um, like the, yeah, I'm not sure exactly. I understand your question.
So I think it was you did like a pie chart of
Okay.
kind of the range of the
Okay.
scores.
Okay. Yeah. So yeah, I'll probably let me take a quick look. I can just mention about that. So yeah, so on your exam, the average is it's not too bad. It's like 69%, which I consider that's actually pretty good. Okay, so typically, this one, yeah, that's the previous classes they score about the same, but slightly slower, lower actually than you guys. Okay, so I would think that's actually you guys did very good in exam too. So they were let me see. I think there were two of you guys in the have the scores in the 90s. Let me just open up my file on my end to be sure about the numbers. Yeah, two of you guys have the scores in 90s, and four of you guys have it in 80s, like 80 between 80 to 89, and then eight of you guys are in the range of 70s. Six of you guys are in the range of 60s, and then five of you guys are in the range of 50s. Two of you guys actually score below than 50. There were two students haven't taken the exam because they were either in quarantine or was sick last time. Okay, so but it's most of you guys have done the exam, so that's why I have four right now. Okay,
Thank you.
all right, you're welcome.